Okay, now I'm going to describe the general method for solving second-order linear homogeneous differential equations. Okay, so this will be the way that you're going to solve on the exams. So how do we do this? Well, by constant coefficient means that all these coefficients are constant. So a y double prime plus b y prime plus cy equal to 0. This is the type of differential equation that I'm talking about. Equal to 0 means it's homogeneous. That's what this means. Linear means all of them have powers of 1. Constant coefficient means a, b, c are constants. Okay? So how do we solve such a thing? Well, what we do is we just plug in e to the rx into this equation. But actually, we will not even do this. We will even skip this one, because if I plug in, I already know what equation I'm going to get. What equation are we going to get? Every time you differentiate, r will pop out. So from y double prime, you're going to get r squared. From y prime, you're going to get r. And from cy, you're not going to get anything. So this is what you're going to get. So if you plug this into the left side, you're going to get this times e to the rx, but e to the rx can never be 0, so you get this. Okay? So you get a r squared plus br plus c. And it's a quadratic equation, right? So you can solve it, right? So but quadratic equations don't always have real solutions. What can happen? There are 3 cases that can happen if you have a quadratic equation. First, you can have 2 distinct solutions, right? 2 distinct real solutions. What else? What else can happen?
Not real.
You can have 2 complex solutions, not the solutions that are not real. What's the third case? The third case is when the 2 real numbers are the same. So you have one solution of multiplicity 2. That's what's going to happen. Okay. All right, and then and thankfully, people who lived before us, who probably died by now, studied these differential equations, and they categorized what kinds of answers they could have, right? And all we have to know is just memorize them and just plug them in. And it's kind of like cheating, because you're just memorizing the answers and just saying that these are the answers. You do still have to solve this, so there is some calculation involved. It's not totally guessing. You still need to do some educated guesses, but it's not really solving. But it's okay. We have these mathematical theorems about independence, linear operators, and uniqueness, existence. All this huge theories proved by mathematicians helping us, so that we can just gladly write down the guessed answer, and we're happy. Okay. So let me write down those suggestions made by those deceased mathematicians, and it's like this. So first, if you have so case 1, if you have 2 solutions R1 and R2, which are different, in that case, you're just going to simply write y as C1 e to the R1x plus C2 e to the R2x. And we've already seen an example that's like this with when we had 1, negative 3, and negative 4. We solved it. We got the 4 and negative 1, right? So that's an example when this happens, right? Okay. Now, case 2 is when your 2 solutions are equal, and it's a single solution of multiplicity 2. Now, in that case, we can't use this as a solution. What goes wrong? Why can't we say this is the solution for this case when R1 and R2 are the same?
1 equals 0.
No.
Well, you get 4 equals C2.
What?
That makes C1 equal to C2 also.
it doesn't make them equal.
Negative.
I mean,
Negative.
the functions become equal. And what's bad about it? Then these two functions are not linearly independent. They're the same thing. And you need two independent ones, okay? So if this happens, we can't say the other one is R2 because R2 is same as R1, and you don't have two distinct solutions to say here we have the generic solutions. So we have to go out and hunt for some other ones, and people found out that in such case you can just multiply x to the previous solution, and you're going to get the other solution. Okay. Oh, by the way, if you had a third order constant coefficient differential equation, you solve it exactly in the same way. You put EVRX, you end up with this equation, which we call this as the what was the characteristic equation? This is called characteristic equation. So you're going to get for third order, you're going to get a cubic equation for the characteristic equation. And for cubic, you can also have three distinct roots, which in that case, you just happily write all of them. But sometimes for cubic, you may have one solution with multiplicity 2 and another one that's different. Then for that multiplicity 2 one, you have to put an x on one of them to create the other solution. Now, how did mathematicians figure out that this is the one? Well, you actually solve it, right? I outlined the way to actually solve a differential equation rather than guessing. If you go through all that method, you will see that the other one is created by just multiplying by x, okay? So that's always true. And then case 3, when R1 and R2 are given by, if you have complex, if you have a complex solution,
Sorry.
then you have the quadratic formula has plus or minus square root of something. So in general, the solutions, when you have complex solutions, it looks like A plus minus BI. That's how one solution looks like A plus BI, then the other solution will look like A minus BI. And that will always happen if A, B, C are real numbers, okay? So in that case, we could also put those as e to the A plus BIX and e to the A minus BIX. That's possible. It's not wrong, but it makes us uncomfortable because the original equation doesn't have any complex numbers, but somehow your answers turn out to have complex numbers. And later on, if you give special initial conditions, you'll find that even C1 and C2 has to be complex. So it becomes a little crazy. So people decided not to use that as the solution, although it is a legit solution, legitimate solution. Instead of that, people decided to do this. See, what is e to the BIX? Well, this is what? E to the I times BX. And I kind of remember something with this. What was this? This is same as what? Euler identity, anyone? Cosine BX plus I times sine BX. That's the Euler identity, right? Yeah. So the Euler identity says that if you have B times I, this B part will become something in terms of cosine and sine. So after doing figuring this out and doing some kind of transformations, people found out that at the end of the day, you can write down your solution as C1 times e to the AX cosine BX plus C2 times e to the AX sine BX. That's how you deal with this third case. Yes?
So there would be no I before the sign?
Yeah, so I'm skipping some steps where you apply the Euler, and then you also rewrite C1 and C2 as some complex numbers, and you take the real part and the imaginary part. There's between here to there, there's a lot going on. But you know that even we don't care about that, because I mean, at the end of the day, what are we doing? We're making guesses. We're not really solving them, right? So we don't really have to know what went on in between. We just have to know what's at the end, as long as we know that these functions are linearly independent. How do you know these are linearly independent? Wronskian. So what I should be doing at this point is to calculate the Wronskian of this function and that function, and show that that's not equal to 0. Also, calculate the Wronskian of this function and that function, and show that it's not equal to 0. But it's a boring calculation. Let's say it's a homework, and I'm not going to collect it, but try it at home. Try to see what the Wronskian of these two will be. It could be on the exam. I mean, it's a simple calculation. So this one, it's very nasty. I wouldn't even do it at home. Okay, but this one, it's kind of cute. So you can try this one. For R1R equal to, say, 2x, so e to the 2x times x times e to the 2x. Try those two and compute the Wronskian. You will see that indeed they are linearly independent. And if it's linearly independent, it's a kosher solution. We can accept it. All the mathematical theories will help us to justify it. Okay, so that's how it works.